Welcome to the Space Telescope Public Lecture Series. Tonight's topic, Exploring the Origins of Planetary Systems with JWST. Our speaker, Nicole Arulanantham of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers from the Office of Public Outreach here at STSCI. And as always, I thank my wonderful tech team, Thomas Marufu and Grant Justice, for doing the recordings and getting these out to you on the various websites. Our upcoming talks in July, on July 2nd, The Pillars of Creation, Multi-Wavelength and in 3D, by that auspicious character, Frank Summers from the Space Telescope Science Institute. I'll be telling you about the latest visualization that we have done of that iconic object and giving you lots of details about the Pillars of Creation. On August 6th, we have a special talk about year 2 in review, the second year of the James Webb Space Telescope, groundbreaking science discoveries by JWST, and that's from Macarena Garcia Marin, also of the Space Telescope Science Institute. And in September, the other space telescope that we operate on, we do Hubble, we do Webb. We're also the future home, science home of the Roman Space Telescope. And Ori Fox will be giving you a discussion of that. He hasn't given me an exact title, but I'm sure I will post it. I'll post it to our website when he does give it to me. Speaking of such a website, www.stsci.edu/public-lectures. That will get you to our public lecture series webpage. And in the lower left, you can see the links to our webcast, both on YouTube and in our webcast archive here at STSCI. And in the lower right is how you subscribe to our email. You get, I don't know, 2 or 3 emails a month telling you about upcoming talks and reminders when the webcasts have been posted. Also on the website is the list of our talks, each one of them listed. And when you click on the read more, you find all of the information that we have, the description, the speaker, as well as links to the archived recordings on YouTube and on the STSCI webcast site. As I said about email, you can do the announcements by signing up at our website, or you can subscribe to our YouTube channel. That's youtube.com, Hubble Space Telescope, all one word. If you sign up and subscribe, you will get new video notices and reminders of these live events. Finally, if you have comments or questions, you can send an email to us at publiclecture@stsci.edu. Our social media channels are for the Hubble Space Telescope, for the Webb Space Telescope, and for STSCI. We do not have social media for the Roman Space Telescope just yet because it hasn't launched, but when it does launch, we will have it for that. And you can find our channels on Facebook, on X, on YouTube, and on Instagram. The news from the universe for June 2024. Our story for you tonight is the endless variety of planetary nebula. I guess I should have said the seemingly endless variety of planetary nebulae. Now, some of you may not know what a planetary nebula is. Well, when I think of a characteristic planetary nebula, I think of the Ring Nebula. This is in the constellation of Lyra, and it's this beautiful, beautiful structure, this ring of gas and dust. And what is going on here is that central star is not a star. It is a dead star. It's called a white dwarf. And so this is actually the burned out core of a star. And as it collapses to create this burned out core, it actually heats up so much that it blows off its outer layers. And so it's sort of like blowing a smoke ring into space from this dying star. And that when to old astronomers, when they saw something like this with a very, very fuzzy telescope, it kind of looked like it could be a planet, but it was a nebula. And so it got the name Planetary Nebula, but it actually has nothing to do with planets, okay? It actually is the remnants of a dying star. And one of the things I love about the Ring Nebula is it looks really great in this Hubble image, but it looks equally great in this image from the James Webb Space Telescope. So whether you're looking in visible light with Hubble or in infrared light with Webb, you see gorgeous and interesting structures. In particular, when you look at the Webb image, look around the edge, that red ring, and then there's this sort of purple lines streaming away, showing that the material is streaming away from that central star. Now, one of the things that this sort of gives you an idea of, oh, this is a smoke ring, you're blowing a ring of material. And actually, no. What we think that the Ring Nebula probably looks like when it looked at from the side is that it would be more like this nebula, IC 4406. And you can see this has more of a cylindrical shape. A lot of these planetary nebula are what we call bipolar nebula, that the material flows out in two oppositely directed directions, okay? So you create, and you can see that not only in this one, but also in the Cat's Eye Nebula, which has amazingly intricate structure on this, but you can see that it's got parallel views going off, parallel structures going off in different directions. And then, of course, the gorgeous Butterfly Nebula that Hubble released back in 2009. And here it's not really sort of the cylindrical shape, but it's more of this hourglass shape that's sort of pinched at the center. All right. And so for an earlier Hubble press release, we talked about the Southern Crab Nebula. And this has that hourglass shape in spades. You can see it in the very center, but you can also see it in the material flowing out. And so this is one of our artist depictions on the right-hand side of the shape of the Southern Crab. So we have these wonderful bipolar planetary nebula. And so I've been looking at these all my career, and I've like, okay, we've seen a ton of these. Is there anything new under the sun or out or inside the galaxy? Yes, there is. For Hubble's 34th anniversary in April of this year, we released this image. This is a planetary nebula called the Little Dumbbell Nebula. And if you look at it closely, you can see it also has that bipolar shape, right? It's not got that cylindrical shape, and it's not got that tight-waisted bipolar shape. Matter of fact, the sort of belt at the center of it is actually kind of thick in comparison to it. So this is sort of intermediate between the IC 4406, which had the cylindrical shape pretty much, and the Southern Crab Nebula, which had the really tightly pinched waist in this hourglass shape. So this is something lots of fun for me because I get to learn a new shape of planetary nebula through our press release observation for Hubble's 34th anniversary. Okay, our featured speaker tonight is Nicole Arulanantham. She is a postdoc here at the Space Telescope Science Institute, and we've had the pleasure of having her here for 4 years. Those who are ardent in watching every month will remember her because she has done this once before. So this is her second public lecture series. Thank you, Nicole, for coming back. She got her PhD at the University of Colorado and her undergraduate degree at the University of California in Los Angeles. And she has done, as she will explain tonight, all of her work on young stars and planetary formation. She came here, she has a little bit of prestige behind her name. She came here as a Giacconi Fellow, named after Riccardo Giacconi, Nobel Prize winner and the first director of the Space Telescope Science Institute. And in her spare time, she does a lot of things that a lot of astronomers do, running and camping. Although she told me that the name of the group she runs with is called A Tribe Called Run, which is wonderful. And one other thing that's interesting about her is that she really enjoys the Baltimore art scene, going to the various art museums. We had a nice discussion about the Visionary Art Museum here in Baltimore. So, ladies and gentlemen, Dr. Nicole Arulanantham.
Hi, everyone. Thank you so much for joining us this afternoon, and thank you, Frank, for the wonderful introduction. So as Frank said, my name is Nicole Arulanantham, and I have the enormous privilege here at STSCI to use data from both the Hubble and the James Webb Space Telescopes to study the process of planet formation around young stars. And my goal ultimately is to basically map the initial conditions of planet formation from these young systems and try to understand how we end up with the population of observed exoplanets around older stars that are detected today. Now, this population of exoplanets around other stars is enormous and is only growing. And when we look at those planets, we can see right away that not every system looks like our own solar system. We see a huge diversity in the types of planets that form around other stars. And so to highlight this problem, I wanted to show a few examples of posters here to the left from the NASA Exoplanet Exploration Program. These are from the NASA Exoplanet Travelers Bureau of some examples of planets that have been detected around other stars where we don't see anything like this in our own solar system. So for example, uh, we see Kepler 16b, which is a planet that's in orbit around two stars instead of one. Astronomers have also detected planets like HD 40307G, which is called a super Earth because it's a bit larger than Earth, but it's not so big that it became a gas giant. And if we were to visit this particular planet, we would feel a very immense gravitational pull. And there have also been planets discovered like TRAPPIST-1e, which is part of a multi-planet system in orbit around a star that's much smaller and cooler than our own sun. So if you were to stand on the surface of this planet and have a look around, you might see things in a very different way than you would see around our much hotter star. So we look at all of this diversity in the population of observed exoplanets, and we also can see this diversity in our own solar system. And my goal as a researcher is to understand the origins of these planetary systems. And so the goal is to understand planet formation as a whole in the universe. And of course, we also want to know, the big question of what made our Earth habitable and whether we can find any clues to that from Earth's origins. So I wanted to start by sharing this photo that I really love. This was taken by Baltimore filmmaker and artist Margaret Rorison on a trip to Iceland this past January. And I think this photo really captures a spectacular image of our own habitable world. And it's an excellent reminder of some of the ingredients that have made our planet habitable. Now, some of you may have been fortunate enough to see the Northern Lights just this past month. Our sun follows an 11-year cycle of activity, and it's currently at a peak. And so what this means is that our sun is producing more energetic particles than normal, and those particles are coming to Earth and colliding with our atmosphere. And when those particles collide with the atomic oxygen in our atmosphere, it causes the oxygen to produce this beautiful green glow that we know as the Northern Lights. Now, I have never been able to see the Northern Lights, but Margaret planned a very careful trip to go and photograph them. And so this beautiful green glow is the product of a lot of nights of standing outside in the cold and waiting for the perfect shot. Now, when we look at this image, we're reminded, right? We see the glowing oxygen in our atmosphere. And we also realize that Earth has a magnetic field. And this actually protects us from that energetic radiation coming from the sun. It makes it so that our atmosphere doesn't get stripped away. We're able to hold on to it. And it also means that we are not receiving much of that harmful radiation here on Earth. So we have a nice atmosphere, and that atmosphere is protected by a magnetic field. Now, the last thing that I wanted to draw your attention to in this image that might be a little bit hard to see, of course, if you're going to see the northern lights, you need a very dark sky, but we can also see this beautiful river that's running through the image. And this is a nice reminder that part of what has made our planet habitable is the presence of liquid water. Now, keep in mind that this photo was taken in Iceland in January, so I don't know that this is necessarily liquid water that you want to go for a dunk in. But again, this photo is a beautiful reminder of the ingredients that have made our planet habitable. Now, as someone who studies the process of planet formation, I look at this image and I immediately wonder where these ingredients for our habitable world came from. And the answer to this question is rather complicated because star and planet formation happen together. And it's currently a big open area of study to understand where exactly the ingredients for planet formation came from. Now, the process of star formation starts with a giant molecular cloud. And these molecular clouds are pretty stable until something comes along and perturbs them. So, for example, a nearby supernova explosion could disrupt this cloud and cause it to start collapsing. So as the cloud collapses, all of its material will start to condense into a smaller and smaller volume. The pressure will build, it'll start to get really hot, and eventually we'll move to this next stage in this diagram, which we call the protostar phase. So we'll have a newly forming baby star that's beginning to form from this clump of gas and dust. Now, we won't actually be able to see the newly forming star just yet, because it'll be surrounded by this envelope of gas and dust that's falling onto the protostar to help it grow its mass. And you'll see, we actually have a hard time observing this in real life, but in this artist's illustration, we can see the signatures of a disk starting to form around this star. Now, eventually, this envelope of material will either fall onto the star or be condensed into the disk, and we'll move to this phase known as the protoplanetary disk stage. Now, at this point, we'll be able to see the central star, and this is what I get really excited about. I like to spend a lot of time thinking about how the star might influence the process of planet formation. And we can also see these beautiful disks of gas and dust, and these disks contain the building blocks of planets themselves. Now, this disk won't last forever, so the planets will form and eventually the material will either fall onto the central star, again, to help it keep growing in mass, or it will actually be blown out of the system. And eventually we're left with a mature exoplanet system where we have an older star and planets, perhaps like the ones we see in our solar system, perhaps like the really weird ones that I showed you at the very beginning of the talk. And so when we think about where the ingredients for planet formation come from, astronomers are currently using JWST to search for those ingredients in the molecular clouds, in the protostars, and in the protoplanetary disks. And I wanted to highlight a really beautiful result that came out last year. A lot of the data from Webb that I'm going to show in this talk will look like this. So this is what's called a spectrum. And on the y-axis of this spectrum, we're seeing the amount of light. So towards the top of the plot, we're seeing more light, and towards the bottom of the plot, we're seeing less light. And as we move in this horizontal direction, the light that's collected by the detectors is broken up into individual wavelengths. And what's really powerful about this is that molecules and atoms and ices are really only able to absorb and emit light at very specific frequencies. And so if we look at a spectrum and we see that light is missing or that there's extra light there, we can use that information to understand what material is in the system that produced that type of light. And so this is how we can hunt for these building blocks of planets. And so this image is showing the spectrum along the line of sight to the envelope of a protostar. And this is really beautiful work that was led by Melissa McClure, who's a professor at the University of Leiden, or at Leiden University. And when JWST looked towards this protostellar envelope, it was able to see absorption features from ices within this envelope. And so we see signatures of water ice, which is very exciting, and all kinds of larger species that are frozen in this envelope. So they're very cold. And we can see lots of absorption from ices, from organic ices. And so we can see that from the protostar stage itself, organic building blocks of planetary systems have already formed. And we want to understand how these organic building blocks might carry through the protoplanetary disk stage and eventually into the planets themselves. Okay, so we're getting a good sense of where these ingredients formed and where they came from. And we might want to know how they're distributed in our own solar system, right? We might as well start at home when we're going to start looking for these ingredients. And this is something that planetary scientists have been doing for as long as people have known there were other objects in the solar system. In this upper left image here, we're looking at a beautiful image of the moon Enceladus that was taken by the Cassini mission. Now, Enceladus is a moon that's in orbit around Saturn. And Cassini discovered these beautiful little jets of water vapor coming out of the bottom of this moon. So we fast forward to observations with JWST, and a team led by Geronimo Villanueva at NASA Goddard Space Flight Center took an image of Enceladus with the instruments on JWST. And what they found was truly remarkable. They found that Enceladus, this tiny moon that's maybe only 300 miles across, actually fits within this tiny red square in the image. And these little plumes of water vapor that were imaged with Cassini extend as far as 6,000 miles. And so all of this light that was collected by Webb is coming from water vapor that's being blasted out of this tiny moon in orbit around Saturn. Now, what this team found was that a decent amount of this water vapor remains in a kind of a donut shape around Enceladus itself. And the rest of the water vapor goes on to feed the rest of Saturn's ring systems. And so we can see right away that our outer solar system is very, very rich in water. And this has some really interesting implications for understanding how water ended up here on Earth. Okay, so people are working really hard to understand how the ingredients for planet formation and the ingredients for a habitable world are distributed in the solar system. And we also want to extend our observations to planets outside of our solar system. And so you want to understand how common the ingredients for planet formation are in planetary systems around other stars. And this is an area where JWST has made remarkable progress. So this is the spectrum from JWST of the hot gas giant exoplanet WASP-39b. And what this plot is actually showing us is the amount of light that's blocked by the planet's atmosphere. So when the planet passes in front of its host star, the elements in its atmosphere will absorb light from the star. So by the time the starlight finally makes it to Earth, we'll see that some light is missing, and this can tell us about the composition of the atmosphere. So when we look at this spectrum of WASP-39b, we can see a signature of sodium in the atmosphere. We see a few different signatures of water, which is really exciting. We see carbon monoxide, so an important carrier of carbon and oxygen, and carbon dioxide, again, an important carrier of carbon and oxygen. And what was really exciting was the detection of sulfur dioxide in this planet's atmosphere. And so sulfur is another key ingredient that we think is very important for having formed our own habitable world. And you can see sulfur dioxide in the atmosphere of this planet. Okay, so I personally think we're in a very, very exciting time to be studying planetary systems because with JWST, we are getting amazing data that is helping us understand where the ingredients for planetary systems came from. We're getting really beautiful observations of bodies in our solar system, and we're able to study planetary systems around other stars in unprecedented detail. And so I think we're in our very own Spider-Verse era, where we're seeing, for example, water in newborn systems. We're seeing it in the solar system, and we're seeing it in other planetary systems. But when it comes to actually understanding how that water goes from the molecular cloud through the protostar to the protoplanetary disk and to a planetary system, and how things got distributed in our solar system relative to systems around other stars, this is still a very rich, open area of research, and it's an area that's really just ripe for collaboration between all different types of scientists. Now, for the remainder of this talk, I'm going to focus on what the instruments on board JWST are revealing about protoplanetary disks. So remember, I am also a Hubble observer, and so I really like to know what the star is doing. And this protoplanetary disk stage is really amazing because we can characterize the building blocks of planets at the same time that we can characterize the properties of these young stars, and we can start to understand how those young stars influence the process of planet formation. So I'll talk a little bit about how we're working to characterize the water content within protoplanetary disks with JWST. I'll also talk about the hunt for organic molecules. So I showed you that really beautiful image of organic ices in the protostar phase. But when we want to look at the molecules, we'll zoom in much closer to the star to look at the very warm regions where we expect rocky planets to form. And we'll look for signatures of organic molecules in the gas phase. And finally, I'll talk a little bit about our work to measure the disk lifetimes with JWST, which really set the upper limit on how much time planets have to form before the disk itself is removed. Okay, so we'll start with water. Thanks to observations with the Spitzer Space Telescope, we discovered long ago that water is everywhere in protoplanetary disks. Now, this plot is a bit complicated, so I'll walk us through it very slowly. Again, this is a spectrum, but we're actually looking at 4 different spectra. So we're seeing the amount of light, again, increasing towards the top of the plot, and the wavelength of light increasing towards the right-hand side. Now, this top spectrum is what models tell us water should look like when we take spectra of protoplanetary disks. So we see several different peaks of light here as a function of wavelength, and each of these peaks corresponds to a wavelength where water is able to emit light. So this is what we expect our real water spectrum to look like. Now, unfortunately, our instruments will smear the spectrum a little bit. And so we can also make some models of what we'll expect to see with JWST. And so you can see that you can still pick out these individual little bumps in the spectrum. So this is really amazing. With JWST, we'll be able to do amazing work to characterize the properties of the water that's producing these emission lines, we call them. Now with Spitzer made some revolutionary discoveries, but you'll see that the model Spitzer observations were much more smeared. So instead of being able to see 3 individual bumps from water, we would see 1 lump. Or here, instead of seeing several little bands separated, we would only see 1 big one. And in this bottom line, we're looking at a real Spitzer observation of a protoplanetary disk, and we can see, as expected, it looks quite a bit like the model. Okay, so Spitzer was able to observe water in protoplanetary disks, and this is what it looked like. And now we'll have a look at what the real JWST observations looked like. Wow. Okay, this is pretty remarkable, right? JWST is allowing us to map water in unprecedented detail. So here we're looking at the spectrum of water from 2 different protoplanetary disks. So one disk is called GK tau, and that is what this purple curve is showing us here. And the other disk is called CI tau, and that's what this white curve is showing us here. And again, we're seeing the amount of light increasing towards the top of the plot, And so the taller the bump, the more light is being emitted by water molecules in the protoplanetary disk. Now you might notice right away that the spectra of water in these two disks look quite similar in a lot of areas, but we also see a lot of wavelengths where the water molecules in GK tau are producing more light than the water molecules in CI tau. So we're seeing a larger purple curve than a white curve. And we see something very, very interesting when we subtract this white curve from the purple curve in this bottom panel here. You'll notice that the regions where the purple curve is the most different from the white curve are shaded in blue in the top plot. And these blue regions represent transitions of water that will come from colder water. So when the water is cold, it will produce a lot of light at these wavelengths, compared to the top plot where we see these red shaded regions. And when water is hotter, it'll produce a lot of light in these red regions. And so what we've been able to discover with JWST is that this red water looks pretty similar in these two disks. But GK tau has an extra population of colder water molecules. Okay, so you might be asking, why do we care if there's more cold water molecules? Why is this interesting? It turns out this is actually the first indication of icy pebbles being able to transport water from the outer regions of this protoplanetary disk to the inner regions where your star can then heat up the water. So the disk around GK tau, and we're looking at an illustration of this here on the left, is very smooth. And so cold, icy pebbles will be able to drift very easily into the inner regions of this disk. And when they get close enough to the central star, that star will boil off the ice and turn it into water vapor. Now, it won't be as hot as the water that's just sitting there already in the gas phase. And so that's why we see both a hot population of water and a much colder population. So this is water that has just been brought off of the icy pebbles. Now, when we look at disks like CI tau, we see something very different. CI tau is a much more extended disk, and we see gaps in its dust distribution. So this means that any pebbles that are moving through the gas and dust in the protoplanetary disk will get stopped at the edge of that gap, and they'll be unable to deliver water to the inner regions of that protoplanetary disk. So the way to think about this is that the water is being brought from regions where we see gas giant planets in our solar system, and even further beyond that, into the regions where we see rocky planets around our solar system. So even if our rocky planets don't form with very much water, this might be telling us that there's a very efficient delivery mechanism in the more compact disks for bringing water from the outer regions of the solar system to the inner regions. Okay, so this was a really awesome, exciting result. And I told you, I really like to think about what the stars are doing to the planetary building blocks in these disks. Now, we expected that we would only see water in protoplanetary disks around larger, more massive stars like the sun. But it turns out with the sensitivity of JWST, we can actually see water in disks around what we call M stars too. Now, M stars are smaller than the sun, they're less massive. So for example, the planet TRAPPIST-1e that we looked at the beginning of the talk is a planet that's in orbit around a low mass M star. And when we look at the protoplanetary disk SZ114, we can see again that the amount of light that we're getting from this disk increases at wavelengths where we expect water molecules to be producing a lot of light. And so this is really, really amazing because when astronomers are hunting for habitable planets, a key population of planets are the planets around M stars. So because the stars are smaller, the planets are easier to detect. And so we can now see water vapor and characterize the building blocks of planets around those M stars when they're very young. And this will hopefully give us some really important clues about how those planetary systems evolved into the systems that astronomers are observing today, the more mature exoplanetary systems. Okay, so JWST has made some really revolutionary discoveries already to characterize the water content in protoplanetary disks. But what about the organic molecules? Why do we care about organic molecules? Now, we think that organic molecules are some of the building blocks of life. And I'm, of course, not a biologist, but we see some interesting things when we compare the composition of Earth to the composition of the sun. So in this image, we are comparing how much of different elements are in the Earth to how much of those same elements are found in the sun. And this dashed line here tells us where the amount of stuff is roughly equal per unit volume in the Earth and the sun. So you can have a look here and see where your favorite element is. I'm definitely partial to sodium, both because Na are my initials and also because I happen to be a very salty sweater. And so when I'm running, I need a lot of electrolyte drinks with high sodium. But the key thing that I want you to take away from this picture is that oxygen, carbon, and nitrogen are depleted in the Earth relative to the sun. So this means that in Earth, there's less oxygen, carbon, and nitrogen than we would expect based on how much of those materials are in the sun. So this is really interesting. And it can be explained again by the temperature of the protoplanetary disk where the Earth formed. Now, carbon, oxygen, and nitrogen are very, very hard to find in a solid state. You have to go pretty far away from your star for those elements to condense into larger species and out of this gas phase. And so we expect that planets like Earth that formed very close to the star will be depleted in these elements. Okay, so we can use JWST to test this theory and to characterize the distribution of carbon, oxygen, and nitrogen across the innermost regions of protoplanetary disks. Now, we might expect cooler stars to host more carbon-rich environments, and this is because the light from the stars will not destroy molecules that carry carbon as easily as the light from much hotter stars. And so again, this is our same disk called SC114, where we saw beautiful water emission lines. And again, we're looking at the amount of light increasing towards the top of the plot and the wavelength of light on the bottom axis. And we can see some beautiful bumps that are produced by acetylene molecules in the protoplanetary disk. So this is a key carrier of carbon and hydrogen. We also see a lot of bumps from hydrogen cyanide. You'll notice this is HCN, so we see hydrogen, carbon, and nitrogen. And we see this really nice, gorgeous bump from CO2. So this is an important carrier of both carbon and oxygen. Now, when we look at warmer stars with JWST, we see that these are much less carbon rich. So we don't see the wiggles that we would expect to see from acetylene. We see maybe a little bit of emission from hydrogen cyanide and maybe a little bit of emission from carbon dioxide. And so this is in line with what we expect from models, but we're not actually positive that this is always true. So with JWST, we're not only able to detect these molecules in a much bigger range of environments, we can also observe a lot more targets and start to characterize this for a really large population of protoplanetary disks. And so this is work that several different groups across the world are actively working on to try and understand the connection between the host stars and the types of protoplanetary disk environments that surround them. Okay, so we've talked a lot about water. We've talked about hunting for organic molecules. Now let's think about how long protoplanetary disks survive and how much time there is for planets to form from these building blocks that we're working so hard to characterize. Now, it's actually very, very difficult to measure the timescales for planet formation. Now, in this nice chart where we go from our molecular cloud to the protostar to the protoplanetary disk to the exoplanet system, everything is spaced out quite evenly. But we don't detect very many protoplanetary disks that are older than about 5 to 10 million years old. And for context, our own solar system is about 4.5 billion years old. And so the planetary systems spend much more time in this older, mature state than they do in this process of formation. And so this means that it's just hard to capture the exact moment of planet formation and to understand how quickly it occurs. Now, I mentioned that when we look at these protostars, we don't actually see the star because it's surrounded by so much gas and dust and ice in this big, beautiful envelope. And when the envelope eventually is either blown away or collapses onto the star to help it grow, we're left with this protoplanetary disk system. But this disk, again, is not static. We have many different mechanisms that can blow away the material from the disk or pull the material onto the star to help it grow, even as the planets are forming. And it's very challenging to observe the material leaving the disk because at this point, a lot of it has gone, right? We're not looking at a protostar anymore. We're seeing through the material and into the star and protoplanetary disk system. And there has been some really beautiful work to observe material leaving the protostar systems. So this is a collection of data from a few different observatories to characterize material leaving the disk in the system DG Tau B. So this gray and yellow material here is a jet ejecting material. So this also will look like the bipolar outflows that Frank was showing earlier, but in a much different physical system. And we also see carbon monoxide being blown away from the system in a wider angle wind. So we can see these very readily in the protostar phase, but until the launch of JWST, it was much more challenging to characterize this in the protoplanetary disk stage. But with the mid-infrared instrument on board JWST, we can now start to do this. So here we are looking at an image of a protoplanetary disk that was taken with the mid-infrared instrument on JWST. And this particular disk is inclined in a way so that it's edge on. So I've been talking a lot about how in the protoplanetary disk stage, you can see the star, with the exception of if the disk is edge on, right? If the disk is edge on and very highly inclined, then all of that material in the disk will block the light from the star. So in this image, the colored light here is showing where light is emitted from large grains that have settled to the middle of the disk. And these two white lobes are showing where light from small grains is detected. And so these are in a big puffy disk atmosphere. So the small grains are found in the puffy disk atmosphere, and the large grains are found in the middle. Now, if we look at the light that's produced by molecular hydrogen, we see a very different image. So again, these white lines here are showing where small dust grains have puffed up into the disk atmosphere. And we see this beautiful extended emission for molecular hydrogen. And this molecular hydrogen is being blown away from the central star and from the disk in this beautiful wind. And so we can measure the amount of molecular hydrogen that's contained in this wind. And what we find is this wind is blowing away enough molecular hydrogen to make up more than a billionth of the sun's mass each year. We know that the protoplanetary disk is not going to be as massive as the sun, and so this sets a nice timeline for a nice upper limit on the timescale for planet formation. So for example, if your protoplanetary disk started with a millionth of the sun's mass, it would be dispersed very, very quickly. We also are able to detect jets carrying away material from these protoplanetary disks. So this image on the left here is showing neon that's being blasted away from the central star in this beautiful jet. And we can also see hydrogen, and this hydrogen is actually falling onto the central star and again helping it grow in mass. And so the planets that are forming in the disk have to compete with all three of these processes to form before the material is blown away in a wind, a jet, or pulled onto the central star. Okay, so this has been a really whirlwind tour of what JWST is revealing about protoplanetary disks. And before I sign off for the day, I just wanted to leave you with a quick snapshot of some other major discoveries. I've talked a lot about groups that I work with, but there are some other major discoveries coming out of other research groups. And one that's really exciting in particular is this beautiful spectrum from a protoplanetary disk that's very close to a bright, massive star. And so light from that bright, massive star is beaming down on the gas in this protoplanetary disk. And so this program was designed to explore whether molecules could survive in the gas surface of this protoplanetary disk. And it turns out that they can. So if we look at this spectrum, we can see a big peak where we expect to see light from, again, acetylene. So we're seeing carbon and hydrogen in this disk. We see another big peak corresponding to hydrogen cyanide. We see signatures of water, and we see signatures of carbon dioxide. So this was a really amazing data set that showed that molecules can survive even in these very extreme environments. Another really awesome result was this discovery that the radiation from the star, which we expect to change over time, will actually have a corresponding influence on the neon atoms that are present again in the gas within the protoplanetary disk. So in this figure, we're looking at two different observations. So this bottom observation is actually a Spitzer observation of the protoplanetary disk SZ Cha, which was taken in 2008. And this yellow spectrum is showing the same disk observed with the James Webb Space Telescope in 2023. And this green region here is showing where we expect neon to produce a lot of light. And this purple region here is where we expect even more ionized neon to produce a lot of light. And you might notice right away that this ionized neon that we call neon 3 is not nearly as bright in the JWST observations than the Spitzer observations. And we can't just blame this on JWST being less sensitive than Spitzer, right? JWST is amazingly sensitive and it's discovering things that we weren't able to with Spitzer. And so what's happened here is that the amount of X-ray light from the star that's reaching the disk has actually changed in the 15 years between these two sets of observations. And we can see this now with JWST, especially when we compare to the long baseline that we have between Spitzer and JWST observations. Okay, so as you can probably tell from the very large amount of information that's been put into this public lecture, JWST is really revolutionizing our study of the origins of planetary systems. And we're in this really amazing era where we can see the building blocks and the ingredients for planet formation in the molecular clouds, in the protostars, in the protoplanetary disks, across other planetary systems, and within our own solar systems in unprecedented detail. So I hope I've convinced you of how exciting all of this work is, and I will very happily take any of your questions. Thank you for having me.
And thank you, Nicole. You've certainly convinced me that we are really finding all sorts of molecular species in these protoplanetary disks that are leading us into these various pathways to them. I took copious notes and I have a bunch of different questions. Let's see, where do I want to start though? Um, so you talked about the blowout timescales. That was one of the later things you talked about. What we in the business call the T-Tauri wind type phases of these things. Do we have a better handle on what the timescale is before these winds from the star blow out everything based upon Webb observations, or is it still in the old measurements?
So this is still, so a lot of that work is still in the old measurements. So as you
Okay.
mentioned, we have a lot of results where we can't take images, but we can look at, again, those spectra and we can characterize the properties of these winds. Now, the exciting thing about all of the results that I just showed you are that these are the first times that we've made these discoveries in
Exactly.
protoplanetary disks, right? We've only been getting these data for a few years now. And so the thing that will really nail this down is being able to look at larger samples of protoplanetary disks. And that's
Mhm.
work that's ongoing and in progress from several different teams around the world. And so hopefully maybe you can have another Origins of Planetary Systems public lecture in a year or two, and we'll be able to show at a population level what this looks like.
Right, right. So yeah, I think that's a really great point to emphasize for the public that, these are the first observations, but until we have a complete suite of these observations, we can't really give good statistics on what's going on.
Exactly. Our goal ultimately is to understand how planet formation proceeds in the universe as a whole. And for that, we need a lot more observations of a lot more protoplanetary disks and a lot more different types of environments so we can really understand what the driving factors are in producing these planetary building blocks and setting the initial chemistry of older exoplanet systems.
All right, fantastic. Well, we've had some questions in the chat, and Grant Justice and I have looked at it, and Grant is the one who records the questions that are there in the YouTube chat. Hello, Grant. Welcome. You're muted, Grant.
How about now? Am
You
I
are
live?
now. You are here.
Hey! Um, Thank you. And yes, the chat has been going off while you've been talking, so I'll try to grab a few good ones.
Okay, I have
So
plenty more questions. Let me just say that. So if you need a little time, I can jump in with an extra question or two or
okay,
four.
let me you while I get the next one ready.
All right.
All right.
Go ahead.
Yep. Why do astronomers get excited about finding planets around stars that couldn't possibly harbor life? Like red dwarfs, if the planet is outside of the Goldilocks zone, there are flares and other things. What makes it so exciting to find a planet that isn't necessarily like M class?
Oh my gosh, this is such a fun question. One of my favorite experiments to do when I taught introductory astronomy classes was to ask who in the room was born after the first detection of an exoplanet. And as time goes on, right, more larger and larger fraction of the class is born after that time. And the discovery around of planets around other stars is pretty recent, right? Like mid 90s, that's
Yep.
what I want to say. And so it's so funny to think about the discovery of a planet not being very interesting. I think they're all interesting, right? And there are a couple of things that I want to say here. Um, One thing that we're really interested in understanding is really we want to know what makes a world habitable, right? And we have this understanding of what has made Earth habitable, but that doesn't mean that that's the only way to make a habitable planet, right? So these planets could be conducive to forms of life that we only see very deep in the ocean. Or it could be something that we can't even conceive of because we haven't seen it. At the same time, planets in the outer regions of those solar systems can still, sorry, exosolar systems can still influence what's happening to the planets very close by. So for example, in our solar system, we think that Jupiter actually had a protective effect on the planets very close to the star, because anytime anything came crashing in into the inner solar system, Jupiter was able to just slingshot it right away. And so this protected our inner planets from just being blown to bits by things flying in from the outer solar system. And so we really want to know where all of the large bodies are in a planetary system so we can understand the dynamics and we can better characterize the planets that are in that Goldilocks zone, and understand whether they're safe environments to harbor life as we know it.
Right. And
That was
as
a
you
great
pointed out,
question.
yeah, as you pointed out in your talk, that as you go to cooler stars, you end up with more organics. So, I mean, yes, of course, you do have more stellar flares and other things. So, I mean, what is the sweet spot? Is there a sweet spot, of terms of when you get more organics, but it gets too volatile so that you need to, in terms of stellar mass? Does the sun exist somewhere around that sweet spot in terms of having plenty of organics or optimum number of organics for possibly forming planets with life? There's something to think about in
Oh,
those
definitely.
implications.
Yeah, that's a great question. I mean, I guess whatever we had was enough, right? We have us,
Well,
we have Earth.
that's an
And
example of one. So,
yeah, and you mentioned flares, right? It's actually really, really challenging to detect flares around young stars.
mhm,
So the atmospheres of those stars are still pretty puffy, and they'll actually shield any flares that originate much deeper in the star. And
right.
so it's actually very difficult to characterize. We actually really don't know how much the young M stars flare. And so it's quite possible that those organics are shielded very well when the star is young. And only after those ingredients are incorporated into planets does the star start its big flaring stage. Um, yeah, so understanding what made our sun unique is a very complicated problem. And this is something that we're just starting to understand now that we can look deeper into these disks with JWST. We're able to detect species that were much too faint to see with Spitzer.
Cool. All right,
I
Grant, what's
love
next?
that. I have two. I have a correction for the first one. I misread it, but I like where we went, so I'm just going to tack it on to the end. Um, this question was actually about inside the Goldilocks zone, not outside of it. But I like I like the breadth that we got about the outside. So why don't we talk about the inside some? And as a second point, I love the idea of Jupiter goaltending the Earth, like just in general. Like that is a concept that I hadn't really considered, but makes perfect sense.
It's gravitational goaltending, yes.
Yes.
Uh, so
So
I,
what we were
yeah,
talking about before, you had spoken about the outer edges, like too close or too far. Um, would you elaborate a little bit more on something that is in the Goldilocks zone, but still may not be able to support life?
Ah, yes. This is very sad. Well, so, Frank mentioned flaring, right? And again, we're very lucky here on Earth that we have this magnetic field that's able to shield us from any solar flares that might come our way. But it is actually very, very challenging to measure magnetic fields on planets around other stars. There are people who have done this in some very, very creative ways, but we've never really been able to directly measure the magnetic field. And so if you have this beautiful, organic, and water-rich planet that's in the habitable zone around an M star, and that planet doesn't have a magnetic field, that beautiful atmosphere is just going to get stripped away very easily. And that would make it very challenging for life on the like as we know it on the surface of Earth to survive, right? We really need our atmosphere. Um,
and I was going to say what you're commenting on really expands upon what Frank Drake did 60, 70, 80 years ago. He thought there were like seven factors that you had to identify to see if there was life elsewhere in the universe. And as we've grown our knowledge, the number of factors we're thinking about in terms of the presence of water, the presence of magnetic fields, the stability of the star, the number of check boxes that you need to get life. It just keeps growing as the more we know.
yeah, exactly. It's a complicated problem. And we really can't forget about the stars, right? I think it's stars are extremely hard to characterize, and there is a lot of ongoing work to understand the properties of stars across the entire electromagnetic spectrum because this is critical for being able to interpret what we're seeing in exoplanet atmospheres.
All right, Grant, we got another question?
Yeah, absolutely. So let me grab this. What is the closest protostar to us?
Ooh, the closest protostar. That is a good question. Our closest protoplanetary disk is about 50 parsecs away.
Okay.
I must say, I don't personally study a lot of protostars, so I don't actually know what our nearest
Isn't
neighbors
like
are.
the Rho
Uh,
Ophiuchi complex is one of the closest ones. I think that's 300 or so light years away. Um, sorry, I'm speaking in light years because
Yes,
it's
I
I'm in public outreach. I'm trained
I
to
know,
speak in
yes.
light years.
Yes,
Uh,
I always forget
don't worry about
about
it.
the
Don't
light
worry about
years.
it.
Yeah.
We're crossing the
Um,
streams.
yes. Yeah, so we do have some nearby associations that contain kind of a range of stars. The protostars that are being really well characterized with JWST are over in the Orion nebula. And so those yeah, I don't know, Frank, do you know what that is in light
1350 light
years?
years away.
There you go. That's awesome.
I
Yes.
have I've done the Orion Nebula visualization several times.
Yeah. Yeah, they're really beautiful. Yeah, I don't know actually though what the closest one to us would be, the
Yeah,
closest system.
I'd have to look it up on the internet myself.
Yeah, same.
So, but I guess we can come up with it's hundreds of light years probably. Okay.
Okay. Frank, I'll let you grab the next one while I take this
Oh,
question
you
in.
want me to come up with something more? Okay, great, great. Um, I wanted to comment on two things. One, that most of the JWST science is coming from spectra. And as much as we have tried in the Office of Public Outreach to get the public to love spectra, it's, we're doing all sorts of wonderful graphics to try and show off all this stuff. It's really important for people to understand that those squiggly lines just have such important meaning to astronomers and that. Um, can you comment on how astronomers view spectra in terms of getting that out to try and translate the information to the public?
Oh, my heart. I love spectroscopy. So this has always been my favorite area of physics. Um, really, spectroscopy is so critically important because it's really, really hard to take pictures of things. I don't know how many of you have ever attempted to take nature photography with like your smartphone camera, right? It's very, very hard. If you see an owl, for example, really far away in a tree, there's only so much you can zoom, right? And we have this problem on a much larger scale when we're doing astrophysics, right? Some things are just so far away and you're not going to be able to zoom, and you can make a really big mirror and it still won't help your problem. But what we can do is we can build really sensitive detectors that can collect light, and we can learn so much from that light if we look in the right wavelength regime, right? And so JWST and its instruments are designed to look for infrared light. And this is specifically designed to look for warm gas and dust that's producing light that our eyes wouldn't even be able to perceive anyway. And so spectroscopy is really magic, right? It's really the only way that we're able to learn anything about these systems that we will never be able to visit within a normal human lifetime, right? These are so far away that, unfortunately, this isn't Harry Potter. We can't just apparate over to
Well, I
Roa
think
right?
you pointed out in your talk, using spectroscopy, we can measure the temperature of molecules in a disk of things that are hundreds of light years away. That's
Exactly.
just
Yeah.
really cool.
We can measure the
It'll never not be
temperature. We
cool.
can, yeah, it's really spectacular. And I really love all the graphics that have been put together by the Office of Public Outreach here. They're really making spectroscopy cool. Yeah. And I
Uh,
always thought it was cool, but
we're just
Shout out
hopefully
to
you all will
graphic
too.
designers.
Yeah, the graphic designers are doing an amazing job.
all right.
Okay, so I've got one good question and one good question to end on. Do you want to stick one in the middle or just roll with the two we got?
Well, let's roll with what we got.
Okay. Do modern planetary formation models support the formation of any binary planets with a mass ratio closer to 1 in the habitable zone?
Wow, this is quite a question. I am not familiar with any literature that predicts this exact scenario. But that is not because it doesn't exist. That's because there are a lot of papers to read, and I personally have not read about that. There are some really remarkable theorists who are working on this exact scenario, though, including scientists who are at STSCI. There's a whole group of people at the University of Nevada, Las Vegas, my home state, who are working on this exact problem. And so planet formation in binary systems is very complicated. You can imagine when you have two stars, that becomes a very complex dynamical problem. A one-to-one mass ratio is interesting, and I'm wondering whether it's a one-to-one, I don't know, Grant, can you see if it's a one-to-one mass ratio with the stars or with the planets?
There's a little bit of a delay. We'll give him a second to answer.
Okay,
Okay,
in my
sounds
reading
good.
of it, it says that the binary planets would have the mass ratio. So the
Okay.
planets with a
Interesting.
mass ratio of 1 to 1.
Yeah, I am sure that somebody has been able to simulate this. I don't know off the top of my head who, um, but circumbinary. I love thinking about circumbinary planet formation. The very first papers that I worked on were about a circumbinary protoplanetary disk that potentially has a planet shepherding the outer ring. So, but that is we think there's just one planet, not two.
Yeah. I mean, I think the closest thing we've got to this in mass ratio would be Pluto and Charon in the solar system, where, that's what, a 4 to 1 or 8 to 1 ratio.
Yeah, that's a
Um,
great point.
yeah, so we really don't get binary planets with approaching 1 to 1 here in our solar system. So that evidence says, hey, that's awfully a difficult thing to do. And yeah, I haven't really thought about mass ratios amongst the stars too, because this you often think of the multiple star systems as being one big star, one small star, etc. But hmm, hadn't explored that. All right, Grant, you said you had one more question.
Yes. Um, somebody beat me to my normal question this time, so I'm going to ask theirs. Um, so let's see. Boop, 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 boop. What are some of the highest impact observations from JWST that you hope and or expect to see coming up next?
Oh, that's a good question. So there are a couple of programs that were just selected for observations in this coming calendar year that I think will be really, really spectacular. So one program is led by Kimberly Ward Duong, who's a professor up at Smith College in Western Massachusetts. And Professor Ward Duong is going to observe a planetary mass object with JWST, and she's going to look at its circumplanetary disk to characterize the composition and structure of that disk. So that will be really awesome. Another program that I'm really excited to see is led by Professor Jennifer Bergner, who is over at UC Berkeley in Northern California. And she has a beautiful program to map the ice content of protoplanetary disks. And so she'll look at these edge-on systems where the light from the star is blocked, but we can still see the disk very clearly. And her goal is to really understand the chemistry that's happening in this ice phase. So the ices and the really, really low mass forming systems, I think, are going to be amazing to see in the next year or so.
Cool. Which reminds me of a question I didn't ask, and so I'll ask it right now. Well, we have just a couple minutes left. Take this as you can take this
Host
as the last
privilege.
one. So you were talking about ice transport across the disk, and when the disk is continuous, you end up getting the ice transport in. But once gaps start to form in the disk, they're sort of blocked from migrating in. So feeding from the beyond the ice line in the outer solar system into the inner solar system. What do we think is the time scale for gaps to form in protoplanetary disks? We've got some great observations, like from ALMA, of gaps in solar disks. What's the time scale for that to happen?
So
When
it
did
can,
the ice transport have to, how long does it have to take place? Yeah.
yes. So it can start very early. The formation of these gaps happens very, very early, as early as, 1 to 3 million years. So that's very quick in terms of the protoplanetary disk lifetime. But we do see systems like GK Tau, which is one of the disks with the water spectrum that I showed that's very compact. And GK Tau is older than that 1 to 3 million year time scale. So it's had time for gaps to form in its disk. GK Tau and CI Tau are actually quite very similar in age. And so if there are any gaps, they are probably much closer to the star, and so they can't be resolved with facilities like ALMA. And so the gaps can form very quickly, but we do also see this population of compact disks that don't seem to have gaps, and that's an open area of research to understand why they don't.
Right, because if we're going to transport water into the inner solar system, and one of the hypotheses of how Earth got its water is that type of transport. You've only got a few million years to do it, and I know to the public, a few million years sounds like a long time, but it takes a few 100 million years for Earth to form, right? So.
Exactly. The other thing, though, is that, even once everything's formed, you can still have stuff that flies in and collides with planets very close to the star. So there is still hope, right? We can see that there's a ton of water in our outer solar system, for example. But I think it would probably not be very nice for modern day Earth to get hit by a tiny comet, no
Right.
matter how much water it was carrying.
And actually, it's only after the Jupiter-sized planets form that things start getting slingshotted, and you throw everything out to form the Oort cloud. So that would be a pinballing time in the solar system.
Yes, not fun.
But eventually things calmed down and life formed. So we had the luck here.
Yes,
All right.
definitely.
And the
All
more we
right.
learn, it seems the more luck we had.
Yeah, yeah.
All right. So thank you very much, Nicole, for this wonderful tour of exploring other solar systems. We're not being able to fly to them like Star Trek, but we're actually able to use Webb to pull out that information and observe them from here. So to me, this is the best thing we're going to be able to do in terms of that Star Trek experience for now. And you are taking us on that journey, and thank you very much for that. Next month, July 2nd, the speaker will be me, talking on the pillars of creation, 3D multi-wavelength exploration. Thank you all for listening, and have a great day.
All right, you're good.